I've enrolled with edX on a course with a uni, San Diego, to get a certification in graphics programming. Intermediate, so should be challenging enough. And I'm just going to go through it. Let me get the chat room up. So wrong. First thing to change. Test. 1 2 1 2 1 2 1 2 1 2 1 2. Yo yo. Yo yo. Oh, it's funny. Feel like the music is not loud enough. The mic. Let's have a look here. One, two, 1 2. I'm on Linux and I'm just trying to resize a window off a screen you can't see, and it's just, even something like that is not straightforward. Let's get on working. This one I'm back. Well, that was logistically challenging. Sweet, we can start. Easy. What is this computer doing? Let's try that one more time. Nope. Okay, here. This is why it's called live streaming.
Welcome back. In this segment, we are going to go over some of the course logistics and give a brief overview of what the course is about, what the course outline is. First, we introduce the notion of the 3D graphics pipeline. The graphics pipeline consists of 3 stages: modeling, animation, and rendering. First, let's talk about modeling. That is the process of creating geometric models of objects we're interested in. This could be a simple model of an object like a teapot. It could be a complicated mesh of an object like a cat sculpture. Or it could be a 2 billion polygon mesh of Michelangelo's David that was scanned in several years ago by Professor Leboy and collaborators. The next step, if you want objects to actually move, is to consider the animation or the motion of characters. And this is a rich area. We often want vibrant humanoid motion. In other cases, we just want motions of objects from one place to another. The final step is rendering, or creating realistic images given the geometry and the animation. And there we want to simulate the way light propagates in a scene to create effects like realistic and intricate shadow details, such as what you see in the images on the right. In this course, we are going to have assignments that cover the modeling and rendering parts of the graphics pipeline to give you a basic understanding of computer graphics. In this course, we're not going to have time to go into animation in detail. We hope that there will be a future course that deals with that. The first assignment deals with transformations, and the goal there is to place the objects in the world and view them. In particular, you will write a simple viewer that will view a teapot placed at the center of the screen, and you will have to move around the teapot and create images in that way.
Transformations.
The next two assignments deal more with the rendering aspects of the course. So in particular, homework 2 is a scene viewer. And there you want to be able to view the scene the user specifies, and you want to be able to do it with realistic lighting, with realistic materials, and as specified by the user. In homework 3, you will build a ray tracer, which is an offline method to create very visually high quality, visually realistic images by tracing rays that arise from the camera and go through each pixel in the image. I've said rasterize, and I have said ray trace. Rasterization refers to your assignment in homework 2. So rasterization refers to homework 2, and ray tracing refers to homework 3. These are fundamentally two different ways in which you can create images. Rasterization essentially goes through all the geometric primitives and determines where on the screen they should go. Ray tracing does the opposite thing, which goes to each point or each pixel on the screen and determines which geometric primitive that corresponds to. They each have their advantages and disadvantages, namely ray tracing can produce higher quality images but has historically been slower. We'll talk about the distinctions between them later in the course. But the nice thing is that homeworks 2 and 3 present ways in which you can create images of the same screen, same scene, using both ray tracing and rasterization. And this is the
By the way,
basic
anybody
knowledge
just joining
of computer
chat, if you go
graphics.
to edX.org, I'll type it in the chat box. This is where you can sign up for the course. Course sign up. You have to pay. Is edX.org. And course name is on the screen. Let's see here. You can get a discount on the hardship route. Instead of $100, it's like $20. It probably takes a week to get that approved. If you're broke and, I don't know, unwell or something, it's worth looking into. That's on edX.org.
That this course seeks to give you. Let me talk a little bit about assignment logistics. The immediate task you need to fulfill is to complete homework 0. And that enables you to ensure that you have the right kind of code compilation framework set up for all of the assignments. Now, for all of the assignments, including homework 0, we will have feedback and grading servers. And what that will enable you to do is that you submit images that your program has produced. Our servers will compare these to the images that should have been produced and will return you a score and a difference image, essentially noting what the differences are. Now, you may wonder how you generate all of the images that are needed. So the program skeletons that we provide do most of that work automatically. For the ray tracer, you generate the images yourself. And you can submit the assignment multiple times, so you get feedback about what is working, what is not working. You can fix it and resubmit. Only your last submission will be counted. The skeleton code we provide in C++, OpenGL, GLSL for homework 0, 1, and 2 enables you to focus on the parts that you really need for the assignment. At the same time, you do get the chance to write a ray tracer from scratch, so that's a good experience to have. To progress in this course, you do...
What was that?
If it's not working, you can fix it and resubmit. You can submit the assignment multiple times, so you get feedback. The skeleton code we provide in C++, OpenGL, GLSL for homework 0, 1, and 2 enables you to focus on the parts that you really need for the assignment. At the same time, you do get the chance to write a ray tracer from scratch, so that's a good experience to have. To progress in this course, you do need a good programming background in C, C++, or Java. The language doesn't matter that much, but the programming in this course will be in C++. You do not need any prior knowledge of 3D graphics or of programming in OpenGL or GLS.
1:30 in the UK.
Let me say a little bit about the workload. This course is structured to have essentially the same workload as the local Berkeley courses, and in fact we're using essentially the same assignments and the same grading mechanism. And so I have the slide which I use for the local course as well, that it's a course which is a lot of fun and very rewarding to create visual computer graphics imagery, but it does involve a significant amount of work. And there are in particular 3 programming projects in the online course, and all of those do require significant effort, the later ones especially. The course also involves understanding of mathematical and geometric concepts, and we will have a final here, which will be multiple choice, where you will be tested on those. Prerequisites, as I noted, you need a solid programming background, and besides that, you need some basic mathematical skills. So we will have a review of linear algebra in the next lecture, and the mathematical skills are not really more than what you would get from a basic high school course. All of our assignments involve programming on the graphics processor using the GL shading language. An interesting point in the last 10 years has been the development of the GPU or the graphics programming unit, which has made the graphics, 3D graphics programmable and has really enabled a revolution in 3D computer graphics. This course is modern and uses GPUs. So in homework 0, 1, and 2, you will be using GLSL with programmable shaders. Nowadays, shaders are programmable and portable across all platforms, including on your phone, for example. But you may need to set up your environment and compilation framework correspondingly.
Sweet. So where do we go now? Here, right? Yep. So this is people's questions on the course, but that'll probably be for the next page. I think just next. Excuse me.
In this segment, we are going to give a brief...
So just some background. I've been teaching myself graphics programming, game engine, simulation, coding on and off 50% of the time or 40% for the last 2.5 years. No, 3 years, maybe 4, since COVID. So a bit longer actually. But not consistently. But that's just been like very rough learning from books and teach yourself. But this is a nice for a course. I don't think there'll be any new information, but it will just be presented orderly and I'll get a certificate for my endeavours, for the work I already did. My maths is maths is not great, so the first bit might be the hardest bit, and then the code and the graphics should be just a refresher. Also, I'm quite forgetful.
History of computer graphics as part of our initial lecture on an overview and history. The term computer graphics itself was coined by William Fetter of Boeing in 1960. The first graphic systems were developed in the mid-1950s, the US Air Force SAGE radar systems, and they were based on a development at MIT. I strongly encourage you, if you have an opportunity, to look at the video on the history of computer graphics, which was released by SIGGRAPH for its 25th anniversary, which, although somewhat dated, has an excellent introduction to the early part of the field. One of the interesting things I always like to do in this overview is to mention to people that text is in itself a major development in computer graphics. If you read Alan Turing's biography when he was developing the Manchester Mark I, he goes into a lot of details about the future potential of computers, things like chess-playing machines, things like even compilers to high-level programming languages. But somehow, even the notion of text escapes him.
So he saw it all coming.
The Manchester Mark I, in its display, essentially
to create what he saw, and then we did 50 years later. That's the guy who broke the Enigma code from the film The Imitation Game. What was his name? I forgot his name. Benedict Cumberbatch. Benedict.
Yeah, had a bank of LEDs. And so you're just looking directly at the memory and trying to figure out what happens. So going from that to our actual textual displays has been a major advance, and the way in which fonts are designed and the way in which they're displayed in the scene directly at the memory. And the Manchester Mark I, in its display, essentially had a bank of LEDs. And so you're just looking directly at the memory and trying to figure out what happens. So going from that to our actual textual displays has been a major advance, and the way in which fonts are designed and the way in which they're displayed in the scene on the screen in order to create a smooth appearance are some of the very interesting early problems in 2D computer graphics. Of course, textual representations haven't been the main way.
Let me see if I can make this better.
Way in which computers have been used for many decades, and the major advance has been the notion of the graphical user interface. The graphical user interface has an interesting history. It was invented at Xerox Palo Alto Research Center in the 1970s, around 1975. But Xerox did not actually benefit the most from the development of the graphical user interface, so it was first used in the Apple Macintosh and subsequently has become a standard for use of any computer on any computers anywhere. Drawing was one of the early applications of computer graphics. Ivan Sutherland's Sketchpad system, which was developed at MIT in the 1960s and was way ahead of its time. It introduced many of the concepts for drawing in current systems, things like pop-up menus, constraint-based drawing, hierarchical modeling. I've included the link there for a video that shows Sutherland's Sketchpad system. I would very strongly encourage you to look at that after this lecture. Sketchpad can be considered the first interactive computer graphics system, and in fact the first PhD thesis in computer graphics. And it really set the stage for what computer graphics could do. Following that, there was also a lot of interest in the development of paint systems, and the Super Paint system, which was developed by Richard Shoup and Alvy Smith, again at Xerox's Palo Alto Research Center in the 1970s. I've taken these images from the excellent introduction on the website, which are noted here, which Richard Shoup has put together. And this Super Paint system really presages modern software technologies, things like Adobe Photoshop. In fact, Adobe was one of the early startups in computer graphics. And nowadays, of course, we don't think twice about applying general manipulations to images. Image processing has been a very significant aspect of what we see on the screen. We rarely see images that have not been processed in some way. So you can alter images by cropping, scaling, compositing them. You can even add or remove objects. Sports broadcasts for television combine 2D and 3D processing, whether it's showing the world record line at the Olympics, or it's showing on each lane, which swimmer is in each lane, and even showing different advertisements to different regions. All of these things are possible by smart image and video processing. That's been a quick tour of 2D computer graphics, and I've gone over it just to make a point that 2D is not something we typically study in a graphics course anymore, but has really revolutionized the world we live in, and you cannot really imagine a world today without 2D computer graphics. But most of this course is about three-dimensional computer graphics, and I just want to give you a brief history of modeling and rendering aspects in that. Geometric modeling is the process of creating 3D geometry, which can then be used in a computer graphics system. In the 70s and 80s, one of the major developments was the creation of spline curves and surfaces. And these were geometric methods that enabled the Utah teapot, as it's known, to be created. And this was developed at the University of Utah, and was at that time a very interesting model because the teapot has lots of interesting geometry. It's not a genus zero surface. It has a handle. It has the spout. And all of this could be developed with spline models. More recently, there's been a lot of interest in acquiring 3D geometry from the real world and representing it as triangle meshes that are acquired from real objects. And so I've shown you this simple 3D scan I did several years ago of this cat sculpture, and you can see the actual 3D triangular mesh elements there. Nowadays, we've had scans of statues going into billions of polygons. A very famous effort is by Professor Lavoie at Stanford and collaborators, the Digital Michelangelo project, where there were scans of many of the statues of Michelangelo, including a 2 billion polygon model of the David. And geometry is getting ever more complicated and ever more interesting. Next, we come to computer graphics rendering. And so in the 1960s, the challenge was handling visibility. And there were a number of techniques which were proposed. So this is hidden line algorithms, hidden surface algorithms. So what I'm going to show you here is an image where I've just drawn all of the lines on the objects. And this leads to an interesting kind of image because you see that there is no real notion of which object is in front of which object. For example, this is the torus, and if I look at it and I look at the cube or I look at the teapot and I look at the wall, you can see that the teapot should actually be blocking the wall, but I can see the line of the wall through the teapot. And so I have no real way of interpreting which object is in front of each other. That immediately leads to the problem of hidden line elimination. I want to eliminate the lines that I cannot see. And this is a challenge in art as well, to create images that convey the notion of depth perception. So this was a problem in the 1960s, and Roberts and Apple worked on it and came up with something that looks now a lot more interesting because you can actually perceive depth. You can say the cube is in front of the wall, the teapot is in front of the wall. Let me just do a comparison. So here it's very hard to even say which object is in front of which one, whereas here the hidden lines have been eliminated and you have a much better depth perception. And of course, hidden line elimination is one aspect of it. You can also extend it to hidden surface elimination. And so this is addressing the fundamental challenge of visibility, which object is before which object. Sutherland in 1974 wrote a famous paper that reduced visibility to sorting and compared a number of different visibility algorithms in this way.
little pause briefly.
Of course, once I've done this, I can also color the objects, but so far notice that I've just colored them in a constant color, and in particular, this image still looks not so great. Look at this cone here, and what we see in this cone is you can clearly see the different facets or the different triangles which are being used to approximate the cone. Similarly, for the sphere, you can see the polygonal outlines of the triangles and the geometry that's being used to approximate the sphere. So this is not ideal yet. And therefore, in the 1970s, the challenge was, how can we get a nice, smooth shaded image of this geometry? So I'm going to start with the image that I showed you earlier, where you can clearly see the polygonal outlines. And Ari Garreau at the University of Utah in 1971 had a way to deal with these polygonal outlines and interpolate the shading so that it would look smooth. So this is what is known as Garreau shading. It's still used in OpenGL. You know it as smooth shading. And suddenly the images look a lot smoother. And in fact, they look like real curved surfaces, not our computer graphics representations of them. However, they still look like matte or clay, and in fact, they're just still a constant color. So the next innovation by Buitong Fong was the notion of specular lighting, or Fong shading. And Fong illumination and Fong shading, models that still bear his name, are, I would say, still used in 99% of computer-generated imagery. What Fong did was he enabled the use of highlights, which now makes it appear much more realistic, and in fact gives this plastic appearance where you have both a diffuse or body color component and the specular highlight. Thereafter, there's a lot of work. Jim Bling and colleagues did substantial work on curved surfaces and texture, and in the 1974, Ed Catmull introduced the notion of the Z-buffer, or the hidden surface algorithm, that is used nowadays in your graphics cards. Those challenges having been solved in the 90s and 80s and 90s, the next challenge was what was known as global illumination. Turner-Whitted in 1980 introduced the first recursive ray tracing algorithm. It's what you will implement in Homework 3, and you will in fact be able to produce images even better than this one. But transport yourself back to 1980, where we've just seen very simple computer graphics images, and suddenly you have a bubble which is refracting a surface, and you have reflections, refractions, all kinds of interesting visual effects. And this image from Turner-Whitted is really canonical and got many people excited about the prospect of computer graphics, that it could really produce realistic imagery. A second revolution was in the area of radiosity, wherein you could simulate the interaction between the wall and one of the boxes. So in this case, the small boxes, so here and here, they are actually made of neutral gray material. So all of the color is actually reflected from the wall. So the blue wall here reflects energy onto the box. And similarly, the red wall here reflects energy onto the box. And in this way, they have this reddish and bluish tinge. This is a famous image known as the Cornell box. I can just write that down here. It's the Cornell box. And it was developed at Cornell University. Thereafter, Kojia in 1986 introduced something known as the rendering equation, which was a unified way to deal with many of the visual phenomena, such as the images on the left from ray tracing or radiosity, and he produced this beautiful image where all of the color again is coming from the caustics from the green balls, the interreflections between the objects, and all of the objects except for the green balls are a neutral gray color. And in this way, he had a number of visual effects that people found very hard to do in a unified framework. And indeed, much of the 80s and 90s involved various ways to solve the rendering equation, and this challenge to consider global illumination of light from everywhere in the scene remains a challenge to the current day. Furthermore, our goal nowadays is to create photorealistic images, that is, images that look just the way a real photograph would. And increasingly, the challenge is also to do it in real-time photorealism. And that is a frontier that now, for the first time, we are beginning to be able to reach. Finally, I've talked about the history of modeling and rendering. Of course, the history of computer animation and of computer graphics in general is also very crucially important. I would highly recommend this clip. I've given the URL below, which has an excellent 10-minute clip from the video on the history of computer animation. And it covers some of the topics we've discussed, so in particular sketchpad, animation, basic modeling, and rendering, and really gives you a good synopsis of what 3D computer graphics and this course is about.
Hey all. Feel free to hit subscribe. I'm going to go through the whole course, I think, this next 2 weeks. Where's the YouTube clip? Is it there somewhere? Yeah, I think the video link expired. Oh, did I miss?
Welcome to these online lectures for computer graphics.
Yeah,
I am Ravi Ramamurthy, a professor at the University of
nearly 2
California,
AM
San Diego.
So hit subscribe if you
Over
want to
the
follow
next
along
several
tomorrow.
lecture segments,
It'll be
we are
a
going
few
to
hours
study
earlier
some
than
of the
the time
beauties
now.
of computer
If you
graphics